And the explanation for the name, I think you wrote of that.
Yeah, it's complex of research, interprofessional, it's French, in aerothermochemistry. Basically, this is a fancy word to say combustion. But we're not only working on combustion, but on everything around combustion. Applied, theoretical, experimental combustion. Okay, so Korea is a research lab which is mainly, not only, but mainly owned by CNRS, the French Research Institute, National French Research Institute, and we are located at Rouen. It's in the northwest of France. So here are some people, Eric, who is in the room, who have more or less worked on what I'm talking about today. And there are two pictures of some nice places around the world, not too far from Etretat and Mont-Saint-Michel. Okay, maybe for those who were here yesterday, I already presented this slide. What are we basically interested in this study? We are interested in expanding three-dimensional flame. And this is, of course, a picture of an experiment, some experiments. And you can see the cellular instability appearing in the flame surface. So how to deal with this kind of phenomenon? Of course, you can do experiments. You can also write some bizarre evolution equations. That's what I'm talking about today, to try to handle the whole surface of the flame and to try to mimic the behavior of the expanding flame. You can also make three-dimensional brute force DNS. Maybe some other codes are even better than this one in the whole world. Ask Andrea. But well, with our simple code, we can handle this kind of 3D simulation, more than 100 million points, and for us it's sufficient. Okay, so what was the story? We wanted to do that, maybe, and in our head, in our brain, we wanted to build some subgrid scale modeling useful for RANS or maybe LES, based on this kind of evolution equation. So we wanted to validate this evolution equation model for two-dimensional steady planar fronts, that's already done, and maybe for 2D and 3D spherical flames. That's what I am talking about today. And maybe after, we would like to do a validation for planar three-dimensional flame. At the beginning of the study, this was not available. Evolution equation for 3D flames was not available. Now it is. So future work will consist in try to validate for planar 3D flames. Why did we choose this one, please? Why did we choose three-dimensional flames, expanding flames? Because we have both experimental results in the literature, but also at Korea. At Korea, we will be able to work with people, experimentalists. We are really making the experiments, so we can talk with them. That was the main reason that we choose this kind of spherical flame, and also because we have an evolution equation model for expanding flames. And of course, the DNS is easy to do in this kind of simple configuration. So, the scientific aim of our work is to check, is to verify, is to validate the method. Is a very simple evolution equation model able to yield quantitative, that means comparable to experiments and comparable to direct numerical simulations. We will see that it's not so simple. Experimentalists do not agree every time. So it's much difficult to say which is correct, which is not correct. To compare, so with homemade, so we can interact with experimentalists, and also to compare these EM results to DNS results, and we can compare them, three of them. I would say the main difficulty of this work is to talk with everybody, to talk with theorists, experimentalists, and people who are making DNS. Talk and try to get something interesting out of that. So, what is the synopsis of my talk? I will present the chosen evolution equation model, which is quite classical now. I will briefly present and analyze the DNS solver developed by Eric Alpin. We will try to compare with experiments with the three approaches, the EM, the DNS, and the experiments, and of course some concluding remarks. So why choosing spherical flames? Because in the literature there is very few or no results for, this is in French, there is no results for flame flame. It's very hard to find results for planar flame, three-dimensional planar flame. But these two people, Renou and Le Cordier, work at Korea. And they made, and they're still making, experiments on spherical laminar and turbulent flames. So we can talk with them.
Excuse me.
Yes.
I paid attention that some topics you wrote in French
yes.
and in English. It is language of appreciate paper.
No. This is because I forgot to translate in English.
Ah.
That's a mistake.
Yeah, I said that maybe it's
no. Everything is in English.
Language of paper.
The papers are in English. Okay. Just a mistake. But I think this is quite easy to understand. Turbulent spherical flames in a cylinder. Okay. How to model turbulent reactive flows? I think you know better than me how to do that. So you can do RANS, of course. That makes an ensemble average of the equation, of Navier-Stokes equations. You can do LES, make filtering. We tried direct simulation. You will see with a simplified model because it's very, very expensive. Or, of course, you can write an equation for the flows. So, many classes of evolution equation model exists based on a perturbative approach. That means that we will try to solve asymptotically the flow equation. Some recent work by Kazakov and Joulin tried a non-perturbative approach, but the equations are quite complex. I can also mention the work by Bishkov and Lieberman. We choose another perturbative parameter, but we do not agree with the equation. Of course, you can also try some other equation, and there may be some variation in the time derivative appearing in the equation. But we wanted to have a very simple equation. Basically, the equation we derived is Sivashinsky equation, basically. And this has been extended to the expanding flame, and also for third order in the small parameter by this PhD student. So what must be the minimal physical ingredients for a viable evolution equation to be comparable with experimental DNS? What are the main physical process? So maybe the main important the more important process is the hydrodynamic instability due to streamline deflection. This is well known since 70 years. Another effect is that the flame tends to propagate normally to itself. It's a geometrical way of propagation. I would call that a Huygens type propagation, and it's of geometrical origin. And there is a third effect. We tend to stabilize the hydrodynamic lambda-Darian instability. It is the thermodiffusive effects coming at the cusps. The cusp will not be like that, they will be smoothed, okay, by this curvature thermodiffusive effect. This is a two-dimensional.
You speak about molecules.
Yes, one thermodiffusive.
What do you mean? Diffusion of gas and mixture, or diffusion of thermal energy?
Diffusion of
Gas
how do you say? Gas molecules,
in presence of
And-
radiator temperature.
and diffusion of heat.
Conduction of heat. It's
And
not
heat.
the same. So, do you speak about diffusion of particles in presence of gradient of temperature? Thermal diffusion, molecular thermal diffusion for definition. It is diffusion of thermal energy, of temperature. It's another story. No, okay.
Here, in fact, this is mainly curvature effects. The fact that you have how to explain that? We will derive an equation for a flame which is considered infinitely thin, but in fact it is not. So you have somewhere to introduce a length scale. And this length scale is linked to the flame thickness. So if your flame is too curved, you will have curvature effects, which resemble, but it's not the same, which resemble a thermodiffusive effect.
But what do you mean when you say thermodiffusive effect? A diffusion of heat, of thermal energy or temperature, or the diffusion of molecules?
Both.
Both.
I have a question. What are on the right-hand figure, what are the color means?
Here,
Yeah.
it's the reaction rate.
So
C'est ça, reaction rate.
So you
Here you have
equation has reaction rate.
reaction rate. Here you see the DNS result.
That's the deal.
That's a DNS result.
Yeah.
So, wait, excuse me, I didn't say that. This is a DNS result. So the flame is resolved. The flame thickness is resolved. And here you can see the reaction rate by color.
That's the homemade DNS.
Yeah, this is the homemade 2D. This is a 2D homemade.
How many grid points do you need inside?
I will talk about this on the. That's a good question. That's a really good question.
Arrows gives the direction of propagation.
Arrows have the velocity field.
Is that the same as the direction of front propagation, or
No. It's the velocity field.
It's the flow.
It's a flow. It's the.
Yeah.
The main
So which direction does the front propagate in that right-hand picture then? How does it front propagate?
I guess the. How do you say?
Up or
Burn
down?
gas are this way, so it propagates this way.
Yes.
No.
Right.
Incoming
Yes,
flow
this
is
is
the problem.
Sorry?
Incoming flow
Yeah, this one.
is the problem. And
Yeah, here you put a turbulent flow. You at the beginning of the simulation you have two flames. One goes this way and disappear, and the other one wants to come this way, but you are blowing. You see, it's going out.
Reynolds number.
Less than 1,000.
Way we are.
Less than 1,000. Ask Eric. He made the
I'm
DNS.
trying to get some numbers.
It would be interesting to see where we are on the. It would be interesting to know where we are.
Yeah.
For example,
It's
in the
4 centimeters height for
no, that doesn't another sense in the diagram of Borghi, for example. Where we are.
It's the la flamelet
Flamelet regime.
regime.
Flamelet regime.
Yeah.
You can see
The chemistry is simplified.
simplifying.
Yeah.
Just one
Single
step
step
chemistry.
chemistry, fuel plus oxygen.
One single step chemistry. Okay. So, here are the mathematics. In order to illustrate the derivation of the method, we will try to begin with a 2D configuration. So we consider two-dimensional front. Okay, and this front will be wrinkled, and it will be parameterized by its main position, that we will assume to be known, and the wrinkling of the front. What we want to do is to write down an evolution equation for this wrinkling of the front, okay? Which must be independent of everything else. That's not true. And we'll see how it's not true, because we have to put somewhere in the evolution equation to input the effect of the turbulence. So what are the assumptions? The front is, of course, infinitely thin. It's an active interface between the burn gases and the fresh gases. The density are assumed constant for the fresh side and for the burn side. Of course, it's a free boundary problem because the active front is acting on the turbulence, which which retroacting after in the front. Okay, this is one. So, how is the method based? It's based on asymptotic expansion, based on small density contrast, which is not true for flames. For flames, this is typically 0.8 or 0.9, which is smaller than 1, but is not small between 1. Okay? This is the idea by Sivashinsky. From this asymptotic expansion, we shall deduce nonlinear, non-local. The problem is elliptic, so it cannot be local. Evolution equation for the local deformation of the front. So, what is the mathematical model? So we suppose we are 2D flow, velocity components 2D, pressure governed by Euler equations for each side. At the discontinuity, since the problem is hyperbolic, we shall have Rankine-Gognot jump relations. Okay, we assume the problem to be periodic, and the curvature and local stretch effect on the local velocity will be taken into account via the semi-empirical law by Markstein.
What is SL?
What is? SL is the laminar flame velocity. Laminar flame velocity, eigenvalue of the problem.
And the flame surface is a single value.
The flame, that's a good point. That's a good point. With this parametrization, we cannot have multi-valued flame. So it's not wrinkled too much.
But it's usual.
It's quite usual. You may have an idea, that's why the IS is really useful, to reparameterize the front, I would say, how do you say that? Russian puppets. How do you say? You can parameterize the front this way, and reparameterize this way. And maybe reparameterize this way, but maybe this is not correct. Mathematically it's possible. Physically I'm not sure it's correct. Okay, so it's for moderately wrinkled forms. So usually you may introduce two Markstein lengths, and what is usually done is that this Sn is the normal flame velocity in presence of a curved flame. You assume that this relationship is correct. So there is only one parameter introduced, is the effective Markstein length. Okay? So this is only a model.
But this parameter is dimensionless.
This parameter is it's length. The
But
curvature.
how is it possible? In left hand side you have
The curvature is 1 over length.
It's dimensionless.
dimensionless.
It's dimensional. LC is dimensionless. C is the curvature, 1 over the curvature radius, and L is the length.
And this is some kind of Taylor expansion or what?
This is made by experiments and theory. I can give you the references.
Asymptotic results. based on very weak strength.
Weak strength. This is
Some kind of
Marstein
regulation.
1950 something. Marstein 1950 something. So
Clavin-
for me, it's
Clavin maybe also did something.
excuse me,
Clavin.
Clavin also.
Clavin.
Yes, Clavin. Yes, more recently. I have the references in the paper if you wish. So for me, it's only how do you say? It will be the basis of the evolution equation. I will show you how. I could have chosen to only say, I don't take into account the curvature effect. So this is 0. And the local, I don't take into account the curvature effects, and I will only choose to say, locally the flame is laminar, and it goes at S of speed, which is not true. So this is a way to introduce the effect of the curvature, still assuming that the front is infinitely thin. Okay. I mean, mathematically, if the front is infinitely thin, you can always think it's locally plane. Understand? But it's not. It has a thickness, so the curvature introduces a reference length.
And why it's second derivative here?
Yes. Yes. So we can write geometrical identities. This is geometry, only geometry, no physics. And if we substitute these geometric identities into this semi-empirical equation, we obtain.
So this is really a semi-empirical equation, yeah? So it's not derived from the first principle. So
I just told you that I can forget this one. This. I just can forget this. Okay, but this is assumed to be. I would say locally. The flame speed doesn't know that the front is curved. So this is a set. It's not true. Okay, the front is infinitely thin. I say no, the front is not infinitely thin, so this velocity is not SL, is SL. Okay? SL. And introduce somewhere a thickness.
L is
So you can also say that this is from asymptotics. Semi-empirical.
L capital is thickness of flame, right?
Which one?
L. Oh, L.
This one or this one?
This one.
This one, yes.
It is thickness.
It's a thickness, it's a Marstein length. It's based on, it's some 10 or to 20 times the flame thickness,
Ah.
approximately. It depends on the few. And for hydrogen, it's negative. For hydrogen, the sign changes. Okay? So these are, I would say, mathematics. If I substitute for the expression or F, capital F, onto the kinematic equation, what I call this equation the kinematic equation, I obtain that. So, the problem is solved.
Any box, where any box? You introduced before any box.
L is the length of the.
There are no any box in the equation.
No, it's how do you say?
Front equation.
It's
Periodic. It will be in the K natural. Okay, let me finish this. Okay, you have this equation. Okay,
written by hands.
written by hand, no resolution. There is no asymptotic for the moment. Nothing has been except maybe this term. But well, assume this is correct. Now what we need to do is to compute the velocity components, u and v, on the fresh side, on the gas, at the discontinuity, on the fresh side. You see? Here you have fresh gas. Here you have bird gas. You need to compute the components u and v of the velocity just at the discontinuity on the fresh side. And what we want to do is to express these components as functional of f. Okay?
I have a question. So in this f equation, essentially your u will be Sm.
No. U and V are the flow equation, are the equation of the flow.
Two components.
Two components. There are two components, U and V, of the flow.
Then your u should appear in f equation.
V,
To the right hand side.
U and V,
Okay.
U and V are the components of the flow. Okay?
V in y direction and U in x direction.
Exactly. Now I need to solve for this U and V as functionals of f. That's why I'm doing an expansion.
Do you have some physical interpretation of different terms here? Or
Let me finish at the end.
No, it's
Yeah,
possible to
this
understand.
is the geometrical origin. Okay, this is the geometrical. This is the curvature terms, and these are the hydrodynamic terms. Mainly.
Say again, one sentence.
This is
okay.
geometry, curvature terms, and physics and hydrodynamic terms. The main difficult connection, the hydrodynamic instability, the main difficulty. Okay, this is the main difficulty. So let's do mathematics. I know you like that. So we can change variable and say capital X equal small x minus f, so that the discontinuity is at capital X equals 0. Okay? So you can write down other equations, continuity, momentum equation, easy. You can write Rankine-Nagel relationships, jump relations. Okay, easy. So the system of equations to be solved is 3 conservation equations for the burn side, 3 conservation equations for the fresh side, and expression of UVP jumps as functionals of the deformation of the front.
how you introduced f inside the continuity equation?
How do you introduce f inside the continuity equation?
The first equation. No. The first equation, the result. Okay.
Because of that. Because of the change of
Because
variable.
of change of variables.
Change of
Okay.
Only it's
Yeah.
tedious, not difficult. Just tedious. Okay? So, what are we looking for? Only for u and v at x equals 0 on the fresh side. So, of course, we need to solve for everything. Well, just have these two components. Okay, a little physics, very little physics. We scale the variables. Okay? So we change capital X and Y with C and theta, time tau, and the from deformation as phi. Okay, we can mix everything and we write the Euler equation this way. And they are the same form, except for the value of alpha star. We change our expression from the burnt side and from the unburned side, the fresh side.
So you neglected viscosity on both sides of the. So you
Yes, we neglect
viscosity.
viscosity. We neglect
So viscosity is important only on the front.
The front is infinitely thin.
Ah, okay. So
How you can
The front is
describe
infinitely so.
turbulence without viscosity?
To my opinion, if you add some viscosity, it will result in a second order derivative terms, and you have already added. So it will change only the parameter you introduce,
But
to my opinion.
Maybe, but if you change to very small scale, it should be something like that.
Okay, it's just
Okay.
a norm. It's just a norm. Okay? Okay. Now we write down jumps in variables, and there are these complicated expressions in phi and the phi derivative. And you can write down in the new variables the equation you are looking for. So no physics for the moment, only mathematics, change of scale. Okay? So now we are developing in powers of alpha. We do the expansion. So we formally develop each term has a power of alpha, and also the jumps has powers of alpha and derivative.
But why you are not satisfied by the last equation? With the strict equation, just before.
Just before?
This
equation is a strict equation if you assume Marstein law. If you assume Marstein law, it's a strict equation.
It's not yet closed, this equation?
No, because you need U and V. You're looking for capital U and capital V as function of phi. Okay?
There are some limiting cases of this equation to the non-known equations or not?
Further,
Are there any transitions of this unknown equation to some limiting cases where we know something?
Yeah.
How you can check this equation? Is it true or not?
This has been studied a long time ago.
Yeah.
I can give you the references. And every limiting case has been validated.
Oh.
Each limiting case has been validated. Many Russian people did that. Vinnikov, Sasorov, Sivashinsky.
Sasorov?
Sasorov.
Pavel Sasorov?
I don't know the first name. I can give you the reference. It's a paper of
Small life,
95.
it's possible to find something very familiar.
1995.
Okay, I don't know. What is the alpha?
Alpha is density contrast.
Okay,
Alpha
this
is
is
delta rho over rho.
I see.
Okay? Supposed to be
1.
supposed to be 0.
So
It's not 0.
Oh, there is.
Supposed to be 0, it's not 0. Okay? So the jumps are written this way, and these are formal developments, formal asymptotic expansions. Okay? So now we try to solve for the equation in HAL. So if we put only alpha equals 0, first order, we have these equations. LR equations are linear and quasi-static. There is no temporal term. Okay? It's very easy. And we can check this equation if we introduce, for instance, we can verify this equation if we introduce, for instance, a potential, a vector potential, velocity potential. And we have a vorticity term in the burnt gas side. And we have to solve the Laplace equation, this is very classical, in the for the velocity potential, and we have jump relations for the velocity and pressure. At each order, we shall have to solve for a Laplace equation for a velocity potential, which is the unknown, and some assumed spatial derivative jumps. The potential z can be decomposed at the sum of its mean value and of a perturbation value. Okay, so we have to solve for this equation. This equation with these jumps. We can solve it. Very easy, very tedious. You can solve this equation via Fourier transform. Okay? And these are only mathematics. There is no physics. This is only mathematics. Okay?
Is exponent enough physical thing?
Excuse me?
This exponent which you find, it enough has very deep physical sense.
Yes, I do agree. I do agree, but I mean, there is no. This is only resolution.
You mean
No, here it's
no
resolution.
additional.
No additional approximation. We are already. The approximation was based on the expansion. Now we are making mathematics. So at first order, we can solve for the solution, and we can find. So we wanted to solve for that. We wanted to solve for the u and the v at 0 minus. So we found them as expression of the v, of the jump in v. And we jump in v, we know it as a function of phi. So the problem is closed at the first order in alpha. And this is approximately Sivashinsky equation. Okay? There is a point I wanted to stress, is that you need, in the solution, here, you need this term. It's very well hidden. You need this term. And this term, you need another information to get it. And this is physics.
Why do you need this term?
To solve exactly the problem. And this term is, at this side, there is no counter term. This term will ensure you that the deformation corresponds to a zero mean flame. That means, how do you, if you have a flame here, you must impose that the mean of the deformation is zero somewhere. If not, how do you mathematically make the difference between this f, okay, and this f with a different mean, non-zero? You know what I mean? You understand what I mean? The same f, but shifted. One is zero mean, the other is not zero mean. Okay? So you have to ensure that mathematically and numerically. That's why you need the mean shape. You need some more information. Mathematically, it means that the k equals 0 mode is not treated the same way.
And the term h as a function of v, this is a source term for this equation?
The what? The term?
Could you show this? No, yeah. The first term in the right hand side.
This
is source term.
This is operator. This is a Hilbert operator.
Yeah, so this is source term for this Sivashinsky
source.
Source
term.
It's done is independent of phi, or it depends on phi?
It depends on phi. Depends on phi. You solve for that, and this v has an expression for where is it? Here. So it depends on phi derivative. Okay. Tedious.
But if we drop alpha, just one term.
Exactly. That's what we found in. Here the Sivashinsky equation. Here is the Sivashinsky equation. Okay. To first order, 1977, Nicholson-Sivashinsky. Second order, Sivashinsky and Clavin. 1987. They make a small mistake. They made a small mistake in their equation. They forgot the counter terms. Third order, a student. Very easy equation. So, why do that? Why? We're not sure. We're not sure. Is it only a formal expansion, or can we prove the convergence? We're not sure. Now we turn back to the physics. Okay. So we have all these equations. Many simple. The first two were very simple. The third one is complicated. So what do we do? Numerics. We can also try, instead of solving Euler equation, we assume the flow to be potential in each side. Okay. We have other equations. And we make steady simulations of the shape of the flame. So this is DNS, Kadowaki, Euler, gamma is alpha. I changed my notation.
0.8. It's not 0.
It's not 0.
It's quite far from 0.
It's quite far from 0. This is the genuine approach by Sivashinsky. Genuine approach by Sivashinsky. So this is wrong. We have no. The solution are supposed to be not correct. Even but tree seems to give good.
But you compare with what solution?
With the DNS.
With the DNS.
With the DNS, the truth.
So you calculate 4 of these fronts, yeah?
You solve Sivashinsky equation with an initial condition, say a sinus, okay? You make the steady calculation, steady solution, and you compare the obtained steady solution with the result obtained by DNS reactive Euler 2D. Okay? Here are the results. So we are disappointed in the sense that Sivashinsky equation is far away from DNS. Okay?
And in this equation there is some kind of average. The average term is
Yeah,
yeah.
Yeah.
What is the average
in space.
Hmm?
It's the averaging in space.
in space?
In space.
But I don't understand.
Let me
There is
finish.
some change with approximation. If we increase the number,
Parameter
the order of parameterization.
The order of parameterization, you mean
Or not
the third order?
parameterization.
The order,
Extension.
the order of the extension. Yes, the equations are different, the results are different.
But we approach the DNS or not?
Not so easily, not so clearly.
Not
Not so
systematic.
clearly. Not so
Well,
clearly.
not systematic.
Not clearly. Okay. Clavin and Sivashinsky show that the S2 equation, second order, has the same structure, not the same coefficients, but the same structure of the S1 equation. Okay? And in fact, the S3, the third order, that the terms almost compensate 2 by 2. That means that the S3 equation, with some fitted parameters, have the same structure of the Sivashinsky equation. That means that S1 equals S2, okay? But S1 also is equal to S3 if you change the parameters. So you can fit the results.
In DNS, what kind of equations have been solved? In
Euler equation, reactive Euler equation with one single step.
So, not this model equation, real equation.
2D?
Real equation. 2D, Euler reactive equation. I would like to finish. Okay, there's a story. I mean, what is the story? The story is, we tried to first order, okay, Sivashinsky equation. Second order, Clavin and Sivashinsky, gives again Sivashinsky equation. Third order, it's not Sivashinsky equation, but if you change one parameter, you can fit the result of S3 by a Sivashinsky equation. Okay? If you change S1, changing one parameter, you can find again the result by S3. Okay? So S3 resembles a Sivashinsky equation if you change one parameter, depending on
which parameter you change?
one of the A, this one. A of alpha. A of alpha.
It's a function.
A functional, yeah. It's a parameter depending on alpha. Depending on alpha.
It's a choosing of function, you mean?
It's a parameter depending on alpha.
Do you know this parameter or
Yeah.
just choose?
Yeah. We can find some relation.
But this function are determined from the theory, in fact.
The theory gives you a parameter.
But
If you change this parameter,
but why it's not correct?
what I wanted to show,
Theoretically, you have some function and you change this function.
Yeah. What I want to show is that the structure of the Sivashinsky equation gives correct results. That's what I want
But
to
the
show.
function is not.
The correct is, the structure is correct, but the parameters are not correct. If you talk to Clavin, he told you it's the same equation. You change the parameter, it's the same equation. Okay, the discussion is open. The discussion is open.
But the form of equation is correct. Yeah?
Okay, the structure of the equation is
Structure.
very robust.
But you change the function.
Yeah, I understand.
You
that.
change
Yeah.
it.
It's
Okay.
not regular procedure.
Maybe you can show this function.
I don't remember this one. It's a polynomial function in alpha. But you can. It's a tuning parameter. For me, you have. What I want to show, if you have one structure, you change one parameter, you can fit DNS results. That's interesting. I would say that's an engineering point of view, not theory. I'm starting from theory, and I have an engineering point of view. I change one parameter, it fits.
But for a given alpha, you have no function, you have a number. So you just change the number. That's
No, if you change alpha, you have the same results. If you change alpha, you change the parameter, and it gives you correct results. So it's a function of alpha, which gives you correct results. So it's not, you can map A of alpha as a polynomial. So this is another result. It's a cut in the you trace yt and f of yt. It gives you a surface. You cut the surface, and you compare the result by S3 and the result by the fitted Michelson-Sebastian-Key equation. And it gives you very similar results. Okay?
So some kind of instability.
Yeah, this is a transient of the. It's not instability. It's the transient. You are. It's the shape you are having after a long time.
And this
Does it mean that the briefly increases?
You started from cosinus, okay? The sinus or cosinus, okay? And you make time very, very long, and you obtain a shape like that. It should be like that. Okay? This is the steady solution of this kind of problem. Okay? You solve for the Michelson-Sebastian-Key equation. Long time, you obtain this kind of solution. And if you look for the time-dependent solution, for each time, you've got a particular shape. Okay? The shape changes with time. You are unsteady, and you cut with this plane, and you have this shape. And the results are very similar.
Why you speak about turbulence? Turbulence cannot be described by error equation.
I do agree completely.
So your result depends on the velocity. Fluid velocity field, yeah?
Here there are no turbulence.
No turbulence.
Here no turbulence. Here no forcing.
No
Forcing is after.
Even no flow in front of the flame.
Why not?
Mean flow. Mean flow.
No mean flow.
No mean
flow.
You are,
Of course, you have some perturbation.
you
no
only looking for a flame. His shape is this one. In the long range, the shape changes and becomes this one.
Okay, but when you solve this equation,
Yes.
I mean this equation which you wrote, this equation depends on the fluid velocity field.
Yes.
In your solution, you use some kind of velocity field.
Yes, I do solve for the velocity. I do solve
by
for the
the
velocity
flame.
induced by the flame.
By the flame. At the moment there are no external velocity.
Okay.
There is no forcing at this stage. There is no forcing.
So flow is produced by flame.
Exactly.
And you solve this equation for the velocity.
Yes, the coupling.
And where produce this velocity? In fresh or in bar?
No, front. Front produces.
It's the front itself. Since the
Everywhere.
problem is elliptic,
Everywhere.
there is
Everywhere.
velocity everywhere.
So you've got some kind of bell from two sides of your front with, or what is the structure of this velocity? Where turbulence in this bell to say?
No turbulence.
No turbulence. But it's no turbulence. Flow. Where flow exists?
What I wanted to show is that the structure of the equation gives you correct results. And now, after, I will put some forcing, some fake turbulence, and it will still give correct results. I don't want to have...
Even for the flame, laminar flame, without perturbations, no flow. You have flow.
I understand. I asked you the trivial
But
question.
if you have non-steady flame, you will have due of potential, you will have the perturbational velocity in front of the flame.
Is it
You will
potential?
never have...
In front of the flame, potential.
Potential.
But behind the flame, it's a
With this approach, you cannot have direct coupling between flame and turbulence. You need another model for that. You need LES.
I see.
You need LES. You need something else.
I would like just to understand your results, nothing else.
Okay. So now I have the DNS, and with the same structure, I change the parameter, of course. The parameter is not the same. I can fit DNS results. That's an engineering point of view. So I suspect the structure of Sivashinsky equation because it gives so good results with first order, second order, third order are the same structure, numerically the same structure. And I can fit DNS results, so I suspect the equation to be very wrong. That's what I claim.
So it's Laminar flame.
Yes, tell me.
But in any case, what I don't understand, really I don't understand, there are another parameter, K-box.
Yeah,
So
the
if
nice
you change K-box, what happens?
the shape will change.
So you can put all curves for any K-box.
I will show you in the 3D case. I will show you in the 3D
They all times the same behavior.
for the 3D case, I tried, how do you say, asymptotic results. Not asymptotic, statistical results.
Okay.
This is very, this shape for this, how do you say, length of the
But the profile is the same.
the profile is the same. You only have one that you can have more than one. If you change your box, you
Okay,
will have
but
one.
even with this, what I don't understand, so you solve DNS.
Yeah,
If we change a little bit the condition of periodicity, what happens? Because it's really some situation, it's just one point. So if you change something a little bit, and you have maybe as a picture,
they are too difficult.
because it's very, it's like religion. Okay, it's just one point. It's quite nice.
Yeah,
But
I want to explain why we do that even further. Why we went further. I explained the whole story. This was the beginning of the story. So we have an hint that the Michelson-Sivashinsky equation was correct. So now we wanted to go further. That's why we were doing that.
Maybe for educational purposes. Sivashinsky equation describes similar kind of effects or not?
Excuse me?
Sivashinsky equation
Yes.
was written for another kind of phenomena, or for
Exactly for that. Exactly
Sorry?
for flame. Exactly for flame.
exactly for flame. Yeah.
Michelson-Sivashinsky.
Why you are so
Michelson-
surprised that you take Sivashinsky equation
Because
just
it's correct
change
at the third order.
with DNS, look, it's a good correspondent.
No,
And
I
was
understand
it
that
good
it's
for
good.
small r, and they
Because-
use for larger.
Doesn't know.
It's his answer.
You have first order. You have
Yes.
Sivashinsky equation. Okay. Second order, you still have Sivashinsky equation. It was not clear that at third order, you still have another Sivashinsky equation.
As a second order input in parameter alpha.
Alpha.
Yeah, let's see.
It was not clear that at third order was still working. And it was unclear that it fits so well with DNS.
Okay.
Of course, that's why we go further. That's why we wanted to make the comparison with three-dimensional expanding things. Before doing that, we have some good information about Michelson-Sivashinsky.
Even with a spheric flame, you have some K-box. Okay.
No.
In some sense, yes, because it's limited. The surface is limited all time. Okay. And for me, DNS, Navier-Stokes equation, has not the same symmetry group like Sivashinsky equation. So to tell that it's the same thing, it's
not the
yeah,
same.
it's not the same
I don't
thing.
pretend. I don't tell it's the same thing.
And for
I just
spheric
tell.
flame, it's the same. You have some symmetry group for Sivashinsky equation.
It's not.
And for DNS equation, it's not the same. So
It's approximate. It's approximate.
Even
I
nonlinearity
know
are
it's
not
not.
the
It's
same.
not exactly the same.
Nonlinearity in
yes,
this
it's
is
not the
different, but
same.
nevertheless
So
it's
maybe
similar.
for some case, it's the same.
Yeah, yeah.
But
I
not-
adopt an engineering point of view.
Mhm.
I don't want to be a theorist. I mean, it's not exact.
but not
It's not exact.
But
because if you go to less, then never you have symmetry. Never.
enough precise.
So this is why
Yeah.
all this question. Because for less, no symmetry. But here, symmetry plays the essential role.
You mean the periodic stuff?
Yes, because for less, never we have this.
Yeah, that's a
Okay.
point.
You
Okay,
want
yes,
boundary
you will
conditions
you
or
will
what?
have to treat the
No,
boundaries.
because for less, as I understood, it's supposed to use this idea for less.
Yeah.
But this idea is based mainly on symmetry conditions. Okay? But with less, never we have this condition.
If you include instead of Euler equation, Navier-Stokes equation
That's
in
what I'm going
DNS.
after.
You need
But with
I'm trying desperately.
Let him finish.
the symmetry condition.
Sorry?
Let him
I'm
finish.
desperately trying. So if you study wrinkling, you study wrinkling with a different size, I would say. You can observe that DNS by another Russian people, Bishkov. Bishkov.
Now it's maybe Sweden, no?
It's in, I think it's in Sweden.
Union.
You can find again with the alpha changing the same results. This ST over SL minus what is the integral of the wrinkling. It's the space integral of the wrinkling. Okay? The wrinkling is the length. If you see the length, instead of having that, you have this shape, and you integrate. I mean, you calculate the length of the.
So
of
you
the
change initial conditions or what? What do you change?
You have an initial condition,
Yes.
okay, and you obtain the shape of the flame.
Yeah, I understand.
And the shape of the flame will give you the surface increase of the flame, and that's it. Okay? And you can observe, but for different alpha and different sizes you have of K-box, you have a good agreement.
Perfect.
A very good agreement. So that's why we suspected. We don't tell this is exact. We tell it fits. It's not the same. It's not this. It's an engineering problem.
Is it
Another
another practical topic?
Other Russian people know. Weinblatt materialism. No, not Russian.
Say this. This guy from Israel.
Materialism is
not Russian.
That's
From
right.
Israel.
Sorry.
He's Jewish.
I think the original wine blood was from
Sorry.
Russia too, but maybe from Russia, who knows?
No.
Okay.
It's okay, and is
Maybe from Israel.
No.
Kn is the parameter introduced for the. Kn is basically 1 over the Marstein length. Basically, Kn is the natural K.
box is a box. Okay.
And the K box is the number corresponding to the length. So you change the length.
And why does it curve behave so strangely towards the left?
That's a good question.
I mean, the data point fits this inverted parabola, right? But not the theory.
Solid lines are given by the equation. The solid lines are given by the
So
equation.
something funny happens.
And
More for large
these
cases.
two guys
Over
said we have, because Michelson-Sivashenki equation has exact solution.
Yes,
We can find exact solution with poles.
yes.
And if you write down analytic solution, you obtain this stuff. But this is unstable.
Sorry, for very large box,
Yeah.
Very
There are
large,
some-
very
there are some
small. You,
problems.
you have the same kind of behavior.
but you have the change of
But we suspect that DNS is not correct here
dividing.
because it's unstable. Analytically, it should be unstable. So that means that DNS has not converged yet.
Mm-hmm.
We suspect that.
Mm-hmm.
Okay. 1 hour. So the simple structure. That's why there are many other equations, but Michelson-Sivashenki equation is very simple and it seems very robust to fit DNS results. Do all these equations differ from reality or from approximate reality? Mainly from their coefficients that you can fit. And as an engineer, you say, okay, I have 1 or 2 coefficients, I must fit them in order to have a real behavior. And how this Michelson-Sivashenki deals with turbulent flows. That's the expanding flames. So for expanding flames, you can write down, maybe it's a little long, you can write down an equation for spherical geometry, spherical coordinates. Okay? So it's a kind of generalization of Michelson-Szymanski equation. And you can have the same kind of terms. You have the geometrical term in spherical coordinates. You have the hydrodynamic term and the curvature term. So you have the same structure. Okay?
What does it mean, hydrodynamic at all? What do you mean?
The hydrodynamic is the Laminar instability. Okay? The curvature effects. And you still have the same parameters, the SL, the alpha, and the K neutral, which are physical parameters.
So SL is
Laminar flame speed. Laminar flame speed. The K neutral is basically the flame thickness, and the alpha is the density contrast. So these are physical parameters. You can have them. You can work. These coefficients, you have to tune them to have a good fit between DNS experiments and this kind of equation. Okay? So you can write, you can decompose the deformation on the Legendre basis. Okay? You can find expressions, you can derive expression based approximately on the same expansion of Michelson-Szymanski for the hydrodynamic and curvature operators. And you can make simulations. Okay? You can add an additive noise. You can add a turbulent noise. You say, okay, in the spherical harmonic basis, we have a first order ordinary differential equation, not partial, ordinary differential equation in time. We have linear terms, Landau value, and curvature terms. These are linear, very simple. Non-linear terms, a square, basically. And forcing, external forcing, turbulence. There is no, at this stage, there is no coupling between this and turbulence. So turbulence is external. There is no coupling. So we can solve that numerically with the exponential time differencing schemes.
So kinematic problem.
Excuse me?
Kinematic problem with a given velocity.
Yeah, exactly. A given velocity field, random.
Yeah.
Random weak. And with this kind of approach, we again have, at more than qualitatively, reproduce results of experiments. You have basically how do you say, suckable flame observed by Groff, for instance, and many others since 1982. So basically you have these shapes that appears at the beginning, and then you have cells here, just like here, appearing suddenly. Okay? We can explain that physically.
Who is Zerdovich and all? It's Boymblatt?
I think it's the big book by Zerdovich. The big book by Zerdovich. You can find that. Many others.
There are 5 maybe persons.
I don't think they're Chinese people.
No, Chinese people.
Okay, you can also, if you increase the forcing, you can observe this kind of behavior. Okay, the same cauliflower-shaped thing with many cells. You can link the size of the cell with the, if you make a cut of this flame, you will find correlated cells.
What is the Reynolds number in DNS?
This is not DNS. This is not DNS. This is EM.
EM?
Evolution equation.
Yes.
This is the solution, very cheap solution of the evolution equation. These are experiments. No DNS yet. No DNS yet.
I have a question. In the experiment,
Yes.
it's a laminar case, is it? The experiments. This is just self-propagated.
This is Pi license Trello 1969. I don't remember it. I think it's very, very small
Do you
number.
remember this Louis number in this case?
It was propane air at 1.17. Propane air.
1.17. Equivalence ratio.
Well,
Yeah,
yeah.
yeah.
5. Excuse me. Equivalence ratio 1.17. So the Lewis number must not be very different of 1.
Lewis number is going to grade label?
No, it's diffusion of heat
Over diffusion of a species.
or diffusion of species.
Oh, okay.
If they do not
The
match,
inverse.
Hartman number, some kind of problem.
Schmidt number, okay.
Squeeze number.
no smooth.
Okay.
Then my question is, in your model, Lewis number, is it
Approximately 1. Say 1. You don't have differential thermodiffusion effect. But you can write an equation.
If I remember, C.K. Law had some review. He said, experimentally, you do not find this cellular type of flames if you have Lewis number.
Exactly. If you have a very small Lewis number, you will not find that.
You say unity.
Unity. I mean, unity, you don't find any.
You don't find any this
Cellular
kind
flame?
of cellular flames for Lewis unity.
No.
Well, for hydrogen, which has
For
has
hydrogen,
number
it's
0.3, yeah, 0.3, then you have this cellular.
Has to be lean for hydrogen.
Has to be lean, yeah.
Has to be
Yeah.
lean, and
Yeah.
for propane has to be rich, I think.
Yes.
What was the
You are
Lewis
correct.
number for that?
It's larger than 1 for propane.
Larger than 1. Okay.
Yeah. And that's why experimentally you have to have rich.
Slightly rich flame.
Yeah, rich flame, then you have this.
So
Lean,
you
reasonable
you
as the one
understand
you
what
have
he's
this.
saying? For species that have Lewis number more than unity,
Yes.
you have to be in the rich regime to have this.
To have this.
Yes. For hydrogen, like for Lewis number 0.3, you have to have lean flames. to
Lean
have
flames.
this.
Okay. So Lewis different than 1.
Yes. Yes.
Lewis one never see this behavior.
Lewis 1 only gives you
Smooth.
very smooth.
Yeah, because it's stable. I mean, this thing is created by the
The
diffusive
thermodiffusive.
instability. Yes.
This is thermal diffusion. And you
The-
have
the point-
dynamic.
The point is that how to have this picture or the other one, changing the noise. For us,
Mm.
the equation is only based on changing the noise.
If you have noise free, you have.
If you have noise free, you have this without the cells.
Okay.
You ignite with I would say you mimic a spark ignition. So you ignite with a random field at the beginning, numerically, and you let the flame evolve.
Well,
With the flame
I don't
involved?
know which knob of yours, but you know these cells, they are created by the fact that okay, for hydrogen, say that for
Yeah.
hydrogen you have lean conditions overall, but then when a curvature forms, okay, on the top of the curvature you will have locally rich condition, richer than the global equivalence ratio, okay, because of the hydrogen diffusing into the curve.
More quickly than
Yes.
this.
While on the cusp, you will have the opposite.
It's the opposite.
You
yeah.
will have the hydrogen going out and having
So
this
you
open
have these
field.
flame caps.
Yes. So you have the extinction at the cusp
Extinction here.
and the rich condition at the top. Okay. So if you don't put in your knob something like this connected to the composition, you will not have this effect. It has to be something related to the thermophysical properties of the
Differential
species.
diffusion.
Yes.
Preferential
But for propane it's the same as he was
But
saying.
On the opposite
On
side.
the other
The opposite
yes.
side.
Usually, Williams is coming, so you can discuss with him. He was talking about that usually differential diffusion and hydrodynamic instability, they help each other.
They help each other.
Yeah, they help each other. So that's why experimentally you do not find from Lewis number, for example, for your propane flame
Yeah.
and a wind flame,
Yeah.
you don't find cellular flame because of this mismatch. So if you keep only hydrodynamic instability, I'm sure you will find
No, I don't think, have you seen this work from Kido, a Japanese group from Kyushu University? They have done a very good explanation of all this for hydrogen and for methane and propane. So they took all the cases and described this very well, I believe. So you can get this. I mean, I think this is very interesting, but you have to adjust the notes with something
That's
physical.
why I'm here. That's why I'm here.
Yes.
If this forcing, uncorrelated forcing, tends to zero, what will be with this soccer ball? It will be.
It will be without the cells,
without
without the small cells.
just smooth ball.
Not with this. This is caused by initial conditions. This I just how do I understand?
So it will be some tesseros,
Exactly. It will be,
but large scale,
and they will stay at fixed angular position.
without any random evaluation.
If you have no random value, you will have this indefinitely,
Indefinitely.
and they will with the fixed angular position. You can explain that by the fact that both the geometrical term and the Landau-Darieux term has no reference length. The only reference length is the K neutral, which is in fact correspond to a very small length, and which will only smooth the shape of the flame. So that's why you have angular position fixed, because you have no large scale reference length if you don't put any noise. If you put turbulence, you will have large scale reference length, which is the integral scale of turbulence, for instance. Okay, and that's observed. That is observed in experiments. In experiments, I will show you. You can have wrinkle staying at the same angular position.
In fact, the experimental work on the preferential diffusion was done by Zeldovich with co-workers. It was in 30 years. And in fact, it's very interesting phenomenon. They took the flame, very unique. So they have a plain flame. It was Dov, maybe it was Dov's name. So and they decrease the equivalence ratio. At some moment, instead, the flame can't continue to exist because global equivalence ratio is outside of stability, flammability. But instead of this plain flame, they observed a small drops, not drops, but spheric flames. A lot of spheric flames.
Flame balls?
Yes, flame balls. It was done in 34, 35, like. It's 8 years ago.
Yeah, but there are more recent work on flame balls by
Yes, but it was done in
Zeldovich showed that.
No, it was done by because
before Zeldovich.
Before.
Okay.
In fact, it's sufficient to open the book Zeldovich, Barenblatt, Machiavelladze, and it was also this experiment is described in this book. It's 35, 34. Okay.
And you have flame balls staying
a lot of. They observe a lot of. Other things that after it was observed in the space.
I used to work on that.
Yes, but it was influenced by the work of Zeldovich.
Of course.
Okay.
Which made the experiment?
And explain all these things.
It's flame caps becoming spherical. The weights.
And
you have
in fact, these bolts have stoichiometric conditions.
Excuse me?
When they have a combustion bolts,
Yeah.
in the flame you have stoichiometric conditions.
You have no. You have only diffusion.
No, but diffusion. But if you calculate the diffusion fluxes,
Yeah.
they are exactly stoichiometric conditions. So
There's a word I don't understand.
Stoichiometric.
Stoichiometric. Yes.
okay. So it's it's very interesting because the flame like some animal who can survive. It's very strange like phenomenon because the flame can't continue to live like plain flame.
Yeah.
It breaks up in small,
Very small.
very small. The flame
You
continues.
have experiments done by
Certain.
NASA in 80 something. I mean,
Look,
2000.
look first.
Running.
Look first.
Yeah, yeah.
Look
Running.
first.
Yeah,
The
the very
very
first,
paper.
the very
Yeah.
first were
And the Deutsche,
It was done before.
Yeah.
Very nice.
the Deutsche explained this experiment.
Differential diffusion.
preferential diffusion.
He
There was-
derived some model for.
Oh, no, but it was explained very simply,
Just,
like usual.
Yeah.
Everything easy.
And after Mark Stein, he explained also by preferential diffusion. He explains what is not here, that the dimension of cells is defined also by preferential diffusion. If there are no preferential diffusion, there are no cells.
Okay.
Really, it was explained by you.
For flame balls, you have also evolution equation modeling.
But
It's integral differential equation for flame balls. Okay, I don't know if I have still the time to just present the DNS solver, maybe not. Okay, I will leave that to Eric. What was interesting? Okay, let's talk about it. Now it's purely numerical. Purely numerical. We wanted to solve for three-dimensional Navier-Stokes reactive equation. And we wanted to do it for a huge flame, the biggest flame we can handle, 3 centimeters. That's not so huge. Too big to compare with experiments, to compare with EEMs. So we change a simplified closure model. Very simplified. Single flat kinetics. Okay? Very global transport. Very, very, very simple. And usually, this kind of DNS are made with collocated arrangements. That means that all variables are defined only on a unique grid. All variables, the rho, the velocity components, the pressure, the temperature, they are all defined on the same grid. And there are other methods, maybe first introduced in 1965, that consider that you can have some variables, for instance, the velocity components, stored on staggered grids, half a delta x staggered grid. And it changes a lot of stuff. What we did is to combine these two approaches, because in our problem we have to handle boundary conditions. So it seems a very natural, a very simple way to handle boundary conditions, to simply add one point at boundaries. We would say it's very easy, it's very simple, but it changes everything. I mean, in the stability, in the precision of the calculations.
So in the interior, everything is the same.
Excuse me?
In the interior, everything is the same.
In the interior, it's staggered.
It is staggered.
It's staggered.
Mhm.
Only at the boundaries that you add a point to completely define, unambiguously define the boundaries.
Yeah, yeah.
So we had, so in 2D, in 3D, we had some more points.
But there is, when you describe pressure, gradient zero kind of boundary condition, you have difficulties.
Zero gradient of pressure.
Oh, zero gradient of species.
We only, for the moment, we only treated outflow conditions. For the moment, there are another student. DNS. We there is another student working on walls, which will be coming next week, I hope. And there's still problems. What I wanted to say is, with this strategy, very simple, maybe I have no time to be very explicit about that, we can handle, we can actually double the number of points in each direction, of effective points. Not the number of points, the number of the length in each direction for the same number of points. Do you understand what I mean? By having a staggered grid and by treating the hybrid with adding some points at the boundaries, we can make the same physical simulations with approximately half less points, grid points, in each direction. So for 3D,
But this is the same as staggered grid.
it's staggered grid. So, unless that we didn't find in the literature any boundary condition treated correctly with this staggered grid. Every time it was periodic, or there was a trick to manage to have the boundary. And when you add this point, it changes the matrices, it changes the, at the boundary, it changes the way you treated the stuff. It seems very simple, very natural. The difficulty is how to handle these different grids. And it gives much better results than simply staggered or collocated grids. You see, if you want to calculate a derivative, the very easy stuff. Let's calculate a derivative with the explicit finite difference, Padé implicit finite difference scheme, or collocated, staggered, or hybrid. So we have 6 schemes.
Or
Okay?
fourth order, sixth order, you say?
6 schemes.
The other one, yes. And the previous one?
We have explicit,
And that's fourth order, yes.
Padé,
Yes.
and we have 3 schemes, collocated, staggered, and hybrid, which is only 1 point
Yeah.
more.
In which order is that done?
Excuse me?
In which order is your semi-staggered one, the new scheme? Which
The-
order do you have for your...
6. For the new scheme is 6th order in space.
Uh-huh.
Okay? And we classically calculate the transfer function for cosine and sine function. Okay? If we calculate the derivative of exponential I omega n, we have the exact solution. Very easy. And this is the numerically obtained solution. We can calculate the transfer function for inner points. So this is, I would say, well known. For the hybrid or staggered, and the inner points is the same.
The second row is the other one, yeah? What is that?
Excuse me.
Oh, no, sorry.
For the hybrid or staggered,
Yeah.
we have the same transfer function, and for the collocated, we have another transfer function. We can compare that with the exact solution for the Padé 6 or for the finite difference in 6th order explicit scheme. And what we have inside the point is that we can manage to get the advantage of the staggered scheme with the collocated scheme. Some points, some variables will be calculated with this scheme. Other variables will be calculated with this scheme and then interpolated in another grid. Some variables will be stored in one grid, but you need another variables from another grid to calculate their gradient, their derivative. So we have to handle all these simple equations, simple operations. What's interesting is that if you add one more point at the boundary, you don't need to interpolate. The idea is very simple, very natural. So, at boundary points, for the hybrid scheme, there is no error. But for staggered scheme, you have a huge error. And you also have a quite huge error for the derivative compared to the hybrid.
Why do you, I mean, I thought for the hybrid, you would still need to interpolate in the interior if you needed to. I mean, if you need the points on the shifted mesh in the interior, you still need to interpolate, and then you have an error.
Yeah. So when this is only for derivation, and we need for the. So you introduce an error by interpolating, and
that's everywhere.
That's everywhere.
Yeah.
So what boundary condition are you talking about?
Outflow.
It's not a periodic condition.
If you have a periodic condition, you don't need to interpolate.
What do you mean by outflow condition?
Ask Eric.
It's open boundaries, but we can
Not
also
directly.
do inflows like NSCBC or triple NSCBC UAT.
We wanted to treat outflow condition for an expanding frame. Okay, so we didn't want information to be reflected by the walls. This is classical. This is completely classical, and we wanted to build a very inexpensive code because we were limited. We wanted to have the biggest calculation possible. Okay, this is, I would say, the motivation of this work. How to construct, how to build a scheme in order to be able to limit the number of points needed.
But can you go back? To this. I mean, you see that the final difference explicit has a larger error towards the high wave number, the PI, okay? But actually this problem you can fix by adding more points.
Of course, you always
Yes. But
if you want
if you have an explicit final difference, it's very easy to parallelize, and so you can add more points and more points and more points, and in the meanwhile you can go to the beach. While the computers get stronger.
The conclusion was it's much easier to parallelize the finite difference than a Palace scheme.
Yes.
We tried to parallelize the Palace scheme, but we said it's not useful.
So in your strategy, in a sense, you have a much more accurate method, but that is not able to take advantage of the multiple. I mean, in the progress of the
because you can parallelize the finite difference. We didn't use the Palace scheme.
You use the hybrid scheme is still finite difference.
Okay.
So it's still easy to parallelize.
Oh,
but you use the staggered
thing
in order to
we use the finite difference staggered hybrid scheme.
Okay, so you don't use padded schemes at all?
No.
Okay.
Yeah, it's for scalar calculation, but for testing in scalar calculation,
okay.
we didn't use that anymore because it was not. You can parallelize it, but it's not efficient.
Okay.
The parallelization is not efficient.
No, yeah. It's that after a certain number of cores, you will have too much expenses for communication.
Okay. Maybe I can go directly to these results. We wanted to simulate 1D laminar method everything, and to see how many points do we need to capture the reaction zone. How many points? Okay? That will give you I would say the delta x. The delta x needed for your simulation. Usually it's given by the flame thickness. You want to capture the flame thickness. So the turbulence will be, in general, will be bigger scale. So how many nodes do we need? For the collocated point, for the collocated scheme, standard, the laminar flame velocity, the exact one was of .38. And if you take less than 20 points in the reaction zone, the collocated scheme is not correct. The collocated scheme. While the hybrid scheme is correct, of course.
And this is exactly why you can go to double the size, right?
Double the size.
Right.
Because here, for our problems, for only 10 points, we have a correct value. So if usually DNS codes are based on collocated method, because it's simpler, and they need something like 20 maybe is not correct because it depends on the way you define the number of points you need to capture the ring. Say 2 times 10 or 5, the number a number of points to capture this velocity. And with the hybrid stagger scheme, you only need half. So in practice, we can make a calculation with twice less point in each direction. And if you take into account the CFL condition, it's a factor of 16. So we don't obtain 16, but maybe 12, because it's not exactly 2. But it's very interesting.
The simulation that I make are with the 8 order, kind of different.
Yeah.
And we have seen that 10 points are enough to predict lambda.
Yeah, I do not agree with that. I do not agree with this point. Originally, it's I discussed with Luc Gardish, and originally here it was 5 and 10. And he told us, no, it's not possible, you need more points.
For 6 order is...
No, it was 5 and 10.
Okay.
It depends on the way you count the number of points. Okay?
So you said you didn't get 16 but 12. Is that due to the overhead because of the interpolation, or
I don't know.
you didn't get 16 times faster, but only 12 times faster?
Yeah, because it's not a factor 2 that you have exactly in each direction.
Okay.
Because the physics is the same. The physics is the same. So you have to capture the same physical problems. How to explain that? The interpretation I think is more correct is that the stencil is more compact. So to calculate the derivative at this point, you only need much points that are very close to this point than for a collocated scheme. Because it works, I would say, so well. We also made a test with an outgoing Gaussian wave. So we have, initially we have the velocity, which is like a Gaussian. And then it goes on both directions. And we wanted to capture the reflected pressure wave coming from the non-reflecting boundary. And what we wanted to have is that after the first reflection, we have no pressure fluctuation coming back. Of course, numerically, it's not true. So at first time, we have a decrease in the pressure fluctuation. At this time, we have these twiggles. That means that the two waves are encountered, and then they go outside. And hopefully, the pressure fluctuation will again decrease. And the staggered calculation by Nagarayan, Lele, and Fretzinger gives this, I would say, poor result. Because I think of the problem at the boundaries. They don't really handle the boundaries. The collocated handle the boundaries and gives correct results. But the hybrid scheme, the very simple modification, has a really improved behavior. So it's very simple to modify that, and we have already much better behavior. Maybe it's known, but we never found in the literature this kind of result. So, okay.
Do you have an explanation why the hybrid scheme was better than the collocated scheme? One would think that collocated would be good at boundaries, right?
the collocated scheme will give you an unambiguous way to define your boundaries. Okay, the hybrid scheme too, but the hybrid scheme will have more compact stances.
Well, it's probably higher order, no? I mean, what is the order of your scheme?
6.
At the boundary too?
No, at the boundary is third order.
Okay. So
The
it's
boundary
same.
is third order.
It's the same for collocated, yes.
It's the same for collocated.
Yeah.
The guy by École Centrale tried the 6th order at the boundary, changing the stencil. One-sided, but the 6th order.
No, 6 orders cannot be.
It didn't
7.
work. It didn't
7
work.
or 3, no? Yeah.
It didn't work at the boundary.
Anyway, it's unstable.
It's unstable.
The high order, 7th order is unstable at the boundary.
So it was very interesting because it's very simple to modify. So this was first attempt on the 3D calculation, and it took 60,000 hours. Okay, so it's at Idris with the French research CNRS, a huge calculator, and you can compare that with the calculation. Yes.
Always turbulent, just from flame and nothing else. No external source of turbulence.
Yes, you see.
Yes,
This is DNS. This is DNS.
DNS and turbulence, just a source of turbulence, just the flame.
No. There is interaction.
Interaction.
Interaction between flame and
You
this
see
is
You put
solution,
external source.
numerical solution of Navier-Stokes
I
reactive
see,
equation.
but you've got random force in Navier-Stokes. How you introduce turbulence?
We have initial field of turbulence, isotropic. We make the
And
turbulence
it dissipates.
decrease. We make the turbulence decrease. We have a Passot-Pouquet spectrum. We have an initial condition,
And this is
turbulence light, and then we iterate, and after we ignite.
but turbulence and the end of calculation disappear somehow.
Yeah, that we can see.
No, but you see, in any way, this turbulence is decaying, no?
Yeah,
You put it in the beginning,
yes,
and
yes,
then
the
it will
decay
decay.
turbulence. So it's so okay. So it's not steering force. It's just decay turbulence.
Just one question. When do you ignite directly at the beginning, or let you first decay?
We let the turbulence decay.
A bit.
So
Okay.
we have I would say a
Good turbulence.
homogeneous turbulence, a good turbulence,
Yeah.
good initial, a real turbulence,
Yes.
a DNS turbulence. Then we ignite,
Yeah.
and we let the flame evolve inside. And as you can observe, that's what I was talking about, the flame tends to become cubic.
Maybe
I don't know if you can see it, but the flame tends to become cubic
What happens on the
because of the boundary condition.
Yeah,
Because of the boundary condition, but the numerical boundary condition. That was another point to be addressed. Okay. Maybe we can compare with a similar calculation by De Goy and Bastians in 2 and others in 2005, and they used 40 microns, a delta X of 40 microns for a flame of 5 millimeters, a cube of 5 millimeters. And here you can use 60 microns. So it was not exactly twice, because of the staggered group. So it's 1.5.
Well, with detailed
Four.
chemistry, 60 micron is a lot. Huh? If you had detailed
It's
chemistry.
not, because it's not really 60 microns. The effective
Okay,
delta
it's
X is something like divided by 2, or divided by something, and it's 40 microns in fact. The effective delta X is not 60. That's the point.
Yeah,
But
well,
also
what I'm
you-
saying, but when you have detailed chemistry and
Yeah,
radicals,
okay.
so you would get problem.
Of course, what I mean is that you would have the same problems with collocated.
Yeah.
With collocated, you need to
Yes,
decrease
yes,
the delta
yes,
X.
yeah.
What I'm saying is that with the slightly bigger delta X than the collocated one, you have
Yeah.
similar results. And it's 1.5 at the 4th power is a huge number for us. We would not have been able to do this calculation without this methodology. Okay? So if you make the cuts post-processing, you can see this plane is quite square because of the boundary conditions. Okay, we did, and it's even worse for laminar planes to get the square shaped plane. By using, okay, I have to talk at least an hour, another half an hour. Is it okay for you, or it's too long because I've been interrupted? I've been interrupted.
Is your equation?
Excuse me?
Is your Sivashinsky equation?
Yeah, I must have to come back. But I was interrupted a long time.
Maybe
Okay.
Coffee break, maybe? Maybe coffee break.
Okay, coffee break. Too long.
Yeah. The boundary condition were NSCBC boundary conditions? Sorry?
It's a UATIM 2007. In fact, I will present that at the end of the month, but it's 3D NSCBC. You get in
All right.
2007, 2007, and in fact, in the
It's somehow about the Laudato. You know,
yes,
Laudato
like
paper?
Laudato, but that's a little bit different because they had also some diffusive terms and reactive terms in the prescription of L4 to allow the flame to go out and to be stable, more stable.
You're right. So in order to have for the flame actually to go through the boundaries itself.
Yes, exactly.
Yeah, because in Laudato you basically do the same thing, but you're not allowing for the flame.
And you have some specific treatments at corners, at edges. For instance, if it is an outflow, here with Laudato you have a specific treatment.
At the corners, yeah.
Yes, at the edges or at the corners.
Yeah.
But with UATIM, this prescription, it is only faces. You have one faces PC, one faces, and automatically this is.
Is that right?
Yeah.
Because I really do. I've been doing the Laudato thing, and I really have these problems at the corners and edges, particularly at the corners.
Yes.
And I kind of didn't have time to follow it. So maybe it's very different then.
But Laudato used it in LES, and I used it in DNS, like UATIM. Then I don't know if problems here to stabilize what's happening at edges or corners can be due to LES sub-modeling.
Yeah, that could very well be right.
Maybe
But then I've been doing the Laudato thing for DNS.
Yes.
And I see the problems. I see the particular problems at the corners where you have outflow and inflow.
Yes. I don't have problems.
You haven't tried that? Well,
yes, I have tried.
You have tried that?
I have tried, and
it works straight away.
I don't have problems with this treatment.
Right. So
but I think that can be due to diffusive terms. Because look, if you do that, it's something like I don't want to make a mistake, but plus L4, 1. If you add the answer here, maybe I should more look at my PhD.
No, right.
Yeah.
Then the talk was you and.
Or later, maybe we can.
You and me. I just need to write you.
But I really like this paper.
In 2007. And what is the journal? Which journal was it?
Computers and Fluids, maybe? Computers and
Fluids in French.
Huh?
You written it in French.
Yeah, I'm sorry.